Hi, my name is Vivian and I'm from Group 4, and today we are going to present our data mining project. Our dataset is about accidental drug-related deaths. So basically, it contains real-world data about people who pass away due to drug-related causes. The main goal of our project is to use data mining techniques to find patterns, understand risk factors, and also detect unusual cases from this dataset. So for today's presentation, we will first explain the background and our research questions. Then we will show how we processes the data, followed by different models including classification, clustering, anomaly detection, and regression. Lastly, we will explain the results, limitations, and also some ethical considerations. Now let's move to the project background. Drug-related death is actually a very serious public health issue. There are many factors that can affect it, for example, different types of drugs, combination of drugs, age, gender, and even time and location. If we only look at the data manually, it is very hard to see clear patterns, especially when the dataset is large. So this is why data mining is useful, because it can help us discover hidden patterns more efficiently. Based on our dataset and assignment requirements, we define 4 main tasks. First, classification to predict whether a case involves fentanyl. Second, clustering to see if there are natural groups in the data. Third, anomaly detection to find unusual or extreme cases. And fourth, regression to predict the age of the victim. So overall, our objective is to better understand the patterns of drug-related deaths and identify high-risk situations. Next, I will briefly introduce our dataset. Our dataset contains around 11,981 records and 48 features. It includes different types of information such as age, gender, race, location of injury and death, cause of death, and also different types of drugs involved like heroin, cocaine, fentanyl, and others. One important thing about this dataset is that it contains different types of data, numerical data like age, categorical data like gender, and also text data. However, the dataset also has several issues. For example, there are many missing values, some categories are not consistent, and drug columns are not in a standard format. Because of these problems, we cannot directly use the data for modeling, so data preprocessing becomes a very important step before we build any model. So now I will explain how we preprocess the data. First, we remove duplicate records to make sure the data is clean. Then we standardize the text values. For example, different spellings like accident all in lowercase, accident all in uppercase, or the A in accident is uppercase are converted into one consistent format. Next, we focus on the drug-related columns. These columns are not in numeric format. Some of them use values like uppercase Y or lowercase y or text descriptions, so we convert them into binary values. 1 means the drug is involved, 0 means not involved. This step is important because machine learning models work better with numeric data. And after that, we extracted time features from the data column, for example, year, month, day of the week, and whether it is weekend. This helps us analyze patterns over time. For categorical variables, we applied grouping of low-frequency categories and one hot encoding. For numerical variables, we applied standardization when needed, especially for models like SVM and k-means, so that different scales do not affect the results. Finally, we define our target variables. For classification, our target is fentanyl. For regression, our target is age. Also, to avoid data leakage, we remove variables that directly reveal the answer. So after all these steps, our dataset is ready for modeling.
So next, we perform clustering using the k-means algorithm to explore whether there are natural groupings in the data. K-means is a simple and efficient algorithm, and it works very well when we want to divide data into groups based on similarity. To find the best number of clusters, we test different values of k, from 2 to 8. For each k, we evaluated the clustering performance using three metrics: Sleuth score, Klein-Stick hypothesis index, and Davis-Bardeen index. After comparing the result, we found that the best number of clusters is 2. Although the sleuth score is relatively low, which means the separation between clusters is not very strong, the clustering results are still meaningful from a practical perspective. Cluster 1 contains the major of the cases with a lower average number of drugs involved. Cluster 2 is smaller, but it has a much higher number of drugs per case and a very high proportion or Horan involvement. This suggests that the cluster 2 presents a high-risk group with more complex drug combinations. We also visualize the cluster using PCA. In the 2D plot, the clusters overlap slightly, but we can still observe that the high-risk group forms or some that distinct region. So overall, clustering help us identify different patterns of drug-related deaths, especially distinguish between normal and high-risk cases. So to conclude, we summarize our findings. The four main tasks. First, the classification model shows that we can efficiently predict fentanyl involvement using structured data. This is important because fentanyl is a major factor in drug-related deaths. Second, clustering reveals that there is a distinct group of cases with more complex and higher drug involvement. This group can be considering higher risk. Third, anomaly detection helps us identify unusual and extreme cases, especially those with rare drug combinations and uncommon characteristics. Fourth, the regression model for predicting ages doesn't perform very well. This suggests that age is influenced by factors not included in our datatest, such as medical history or socioeconomic background. Overall, this project demonstrates a full pipeline of data mining, include data pre-processing, feature engineering, model building, and evaluation. It also helps us gain practical experience in working with real-world data, as well as proving our teamwork and analysis skills. So in this part, we use a linear SVM model to predict whether a death cases involve fentanyl. We choose this model for a few reasons. First, after data preprocessing and one hot encoding, our datasets have a large number of features, and many of them are sparse, so a linear model like SVM is more suitable compared to more complex kernel methods. Second, linear SVM is a relatively fast and stable, especially with our dataset size. Third, it has good generalization ability, which means it can perform well on unseen data. So for the implementation, we split the dataset into 75% training data and 25% testing data. We also use street field sampling to make sure the proportion of fentanyl and non-fentanyl cases stays consistent in both steps. After training the model, we evaluated it using several metrics include accuracy, precision, recall, F1 score, and log-awk. We also applied 5-fold crossing validation to check the stability of the model. The result shows that the model performs quite well. The accuracy is around 0.79 and the log-awk is about 0.86. This means the model has a strong ability to distinguish between cases with and without fentanyl involvement. So from the confusion matrix, we can see that the model is better at identifying fentanyl-related cases. However, it still makes some mistakes when predicting non-fentanyl cases. One main reason for this class imbalance because fentanyl cases are more common in the dataset. Overall, the model is useful for risk identification, especially the detecting fentanyl-related deaths.
Now is the part 7, regression module presentation. In the return mission, we use random forest regressor to predict the age of the deceased. The reason for choosing a random forest is that it can handle non-linear relationships and the interaction between variables. It can provide characteristic importance for interpretation. The experimental results show that the RMSE of the module is 12.1344. The mean is 10.0938, and the R-square is 0.0753. The average R-square of 5-fold cross verification is 0.0467. This shows that the model's ability to predict age is weak. That is to say, relying on the drug combination, location, and time information in the current dataset alone is not enough to explain the age difference well. Age may also be influenced by external factors such as health history, socioeconomic background, or medical status, which is not in the current dataset. Although the regression performance is not high, the characteristic importance results still provide valuable information. The top variables include death month, death day of week, death year, substance count, opioid count, and cocaine, benzodiazepine, ethanol, and other drug markers. This shows that time characteristic and drug combination complexity have a certain impact on age distribution.
In this part, we focus on anomaly detection using an isolation forest model. Isolation forest is suitable for the test because it does not assume any specific data distribution and works well with high-dimensional data. We set the contamination parameter to 5%, which means we assume about 5% of the cases are anomalous. After running the model, we identified 599 cases as anomalous, while the rest are considered normal. To better understand these anomalies, we examined the cases with the lowest anomaly scores. We found that these unusual cases often shared several characteristics. First, they involved multiple drugs at the same time, which makes the drug combinations more complex. Second, they may include rare or less common substances, such as synthetic drugs. Third, these cases often differ from the majority in terms of age, location, or the demographic features. This shows that anomaly detection is useful for identifying extreme or unusual cases that may require special attention. From a public health perspective, these cases could represent high-risk situations or emerging drug trends, so they are important to monitor.
Now for the Part 9 limitation and suggestions for improvements. There are several limitations in this project. First of all, there are many missing values and inconsistent labels in the data. Secondly, fields such as cause of death and description of injury contain rich text information. But in order to avoid target leakage, we do not include them in the main modeling process. Thirdly, category imbalance will affect the classification task. Finally, K-means has limited ability to identify complex non-spherical structures. In the future, it can be improved from the following directions. First, add text mining to vectorize the description of the cause of death and injury. Second, try other classification models, such as logic regressions, XGBoost, or LightGBM. Third, try DBSCAM, hierarchical clustering, or Garcia-Hilbert model. Fourth, compare LOF and one-class SVM for abnormal detection. Fifth, introduce richer external variables such as socioeconomic data or geospatial characteristics. Lastly, I will talk about ethics and responsibility. Since we are working with sensitive data related to death, we need to be careful. First, even though the dataset doesn't contain full personal identity, there is still a risk of re-identification if too much detail is shown. So we should avoid exposing individual level information. Second, variables like race and gender may introduce bias, so the model results shouldn't be used to judge or discriminate against any group. Third, our model is mainly for pattern analysis. It shouldn't be used to make direct decisions about individuals. So overall, ethical use of data is very important in data mining, especially in real-world datasets like this. Okay, the above is the demonstration of our group data mining project. Through this project, we have completed and complete process from data cleaning, feature engineering, module training to result interpretation, and also have a deeper understanding of the complex patterns in real-world public health data. Thank you for listening.